If you have gone through all the videos in the series up to this point, I now deem you ready to move into the advanced TCP/IP section, which as a broad overview really focuses on one concept, and that is TCP/IP subnetting. Now, if you've been in the technology field for a while, you've probably heard of subnetting before. It's just one of those concepts that you can't get away from, it seems like. And a lot of people have many different ways to explain it, and some ways are very confusing, some ways are not so confusing. Some ways get really heavy into math, some ways do not. So what we're going to do is take a few videos to explain what TCP/IP subnetting is all about. Now, the beauty of having this on CBT Nuggets is if you ever need more review, you can always come back and watch the videos again and again and again. And there's plenty of practice that we're going to do as well. So the first piece of understanding subnetting is working with binary. So before we just jump straight into binary, I want to do a little bit review of the basics of the IP protocol. Talk about where it comes from, what it does, that sort of thing. Just a quick high-level review. And I'd also like to give you a preview of what's to come around the corner with the next version. Finally, we're going to take some time and look at converting numbers from decimal to binary and back, one of the essential skills you must have for subnetting. Well, let's start off by doing a little bit of review on the IP basics. As of right now, we are using TCP/IP version 4 addresses. Now, there's your trivia question, is to figure out what TCP/IP version 1, 2, and 3 really were. I'll save you some time. There was no version 1, 2, and 3. They just started and really published version 4 to start off with. So an IP version 4 address looks something like this, 10.10.10.10, where each one of these represents an octet. It's a 4-octet address, and each one of them represents 1 byte of information. You'll oftentimes hear an IP version 4 address referred to as a 4-byte address, or more commonly, which we're going to talk about later, a 32-bit address. Now, it can be one of any 3 different classes. Now, there are 3 classes that are usable on our networks today, A, B, and C. There is a class D and E, but we don't use those in our networks. One is considered multicast addresses, and the other one is considered experimental addresses. So based on the address class that it belongs to by default, it will define a subnet mask, which divides that IP address into a network and host portion. So for example, if I had 10.10.10.10, and by default this is a class A address because the first number falls between 1 to 126, this number right here, I know that by default it has a subnet mask of 255.0.0.0. So that tells me that this first 10 right here represents the network this host is on, and these last 3 tens represent the host that it is on that network. Now, with a Class A address, you get one network here, 10, and 16,777,214 possible hosts on that network. Meaning, if every single one of these was to go from 0 to 255, which is the biggest number you can have in an IP address, you'd get 16 million some addresses that you could use. Now, the recommended maximum number of hosts per networks is 500. So with that in mind, you can see that we slightly exceed the 500 recommendation by having the 16 million. That is one of our needs for subnetting, the skill we're going to talk about. So that's what the subnet mask does, is really tell where our IP address divides to break into a network and host portion. Finally, our IP addresses work at layer 3 of the OSI model. They're used for routing. They're used for finding the best way to reach a given destination. Before we get into the binary, I want to give you a preview of what's to come. Right now, we are using TCP/IP version 4. As we speak, as I am speaking to you right now, a major worldwide transition is taking place into IP version 6. Now, I don't know if you've ever seen an IP version 6 address before, but let me show you an example. A lot of people think they're just doing something like this, 000, that's our version 4, and they think, oh, well, version 6 must have 2 more. No, actually, here is a version 6 address. 1, 2, A, B. It moves to hexadecimal, so we now have A through F as valid characters. It uses colons. clicked my button there, uses colons instead of periods now to separate them. So we have, there's our first octet, 215C, 39AA, 54B6, FF6A. Oh, we're still going. 7890, and one more. No, wait, two more. 77AA, and then finally AABC. That, my friend, is an IP version 6 address. Needless to say, we are not going to run out. Well, I'm sure people thought that with IP version 4. They're like, well, how would we ever run out of IP addresses? And yet we have. But with IP version 6, someone far geekier than me actually figured out that with that number of addresses, every square inch of the planet Earth can be assigned 3.7 million addresses per square inch. Every 3 square feet of the Milky Way galaxy could have an IP address using this range. I can't remember the exact statistic because I really don't commit these kind of things to memory. But they actually figured out that you could give somebody the entire IP version 4 address block, with these 4 octet. You could give them an IP address, or sorry, the whole block, all addresses that are in that range, once a second, and this is where the statistic becomes fuzzy, but you would actually still not run out of IP addresses if you were giving them the whole IP version 4 range, every address possible in IP version 4, once a second, and it was something like 700 years. I mean, again, I can't remember the exact, so don't quote me on that, but it's something stupid to where IP version 6 is going to blow it away. Now, if you've seen subnetting before, you might be thinking, well, when we get to IP version 6, we don't have subnetting, right? Because there's so many addresses. Oh, we do have subnetting in IP version 6, and it's very similar to what we're going to do in IP version 4. It's just things get bigger. Now, a preview of what's to come. This is where we go from the technical side to Jeremy's conspiracy theory. I have a feeling in the future that you will see everything on the planet assigned an IP address. Here's my theory. As of right now, the technology exists. They actually wrote an article about this in Scientific American. The technology exists to where everything can be assigned an IP address as it stands today. They already make microwave ovens and refrigerators with IP addresses that have diagnostics run on them remotely by the repair people to see exactly what's wrong with them. They have cars that have IP addresses. They have pets. You can actually have a chip implanted in your pet. And as of right now, it's not assigned an IP address, but it can be. You could integrate that with GPS and have petquest.com or something, where you go and you're like, where's my Fluffy, and you find a little blinking Fluffy icon on the map to show you where Fluffy's at. They actually have, and this was published in the paper probably a couple months ago, over in New York, they have started embedding chips in people. It's a voluntary basis, and it's a chip the size of a grain of rice that's biometrically powered, and my mind immediately is going to the Matrix right now, where they can actually track that person and contain a bunch of information about that person on that chip. The reason that they are proposing this is because primarily of kidnapping. As of right now in the United States, we have this thing known as an Amber Alert, where when a child is kidnapped, they immediately bleep all the TV, the radio, have you seen this child kind of thing. But even that can only stretch so far. Imagine if you could actually pull up kidquest.com, being silly there, but you could actually pull up a website and find out where your child is at and track the child no matter where they go. So that's kind of where I see things going, is eventually everything will be a part of this global network and have an IP address. That's my theory anyway. On that note, we move from conspiracy theory to working with binary. In order to explain how binary works, you need to know where it originated. There was actually a brilliant scientist named Rico. who invented construction bricks that were lightweight, inexpensive, and indestructible. You know, as of right now, we have construction bricks, but they're made of concrete. They're heavy. You drop them, they'll shatter into a bunch of pieces and so on. So Rico created this brand new construction brick and started selling them to the masses. Now, while Rico was a brilliant scientist, and you can see Rico right there in the picture, while he was a brilliant scientist, he was not a very good businessman. So he hired Bob. And Bob actually was his go-to man that would fulfill the orders for the clients. So this guy came up, this first guy right here, and he said, I would like, Rico, 210 of your new bricks. And Rico would yell back to Bob, hey, Bob, 210. And Bob would go, okay, okay. Run across the building, grab one. Poof, put the one on the counter. So you got one brick. And then Bob would run across the building, grab another brick, and run back to the other side, pile the next brick up there. Now this guy is sitting there watching this pile slowly go. He's kind of smiling because he's like, I'm getting my bricks, but man, this is going to take a while. Bob, you can see, frantic Bob over here, just sweat pouring off of him. Now you can see the guy behind him right here asking for 120. He's kind of worried right there. That's my worried face. And yes, I did draw this on my own. Finally, the last man behind him is just angry. He's an angry man because all he wants is 15 bricks. And not only is he the shortest man in line, now that I see that, but he has to wait until all of these bricks get fulfilled before he just gets his 15. So, 50 bricks into this process, Bob finally collapsed and he's like, Rico, close the store. So Rico drops down his little silver gate. Chung, 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 all the customers outside are, what's going on? And Rico resuscitates Bob, and Bob says, we need to find a better process. I can't keep up with this. So I'll tell you what. Something I saw at Home Depot a while back. I want to implement it in our business. We need to palletize. I'm going to create a pallet of 128 bricks. I'm going to create a second pallet of 64 bricks. Third pallet of 32 bricks. These are our pallets sitting up here. Fourth pallet of 16 bricks. See, the pallets are getting a little smaller. 8 bricks. 4 bricks. 2 bricks. Don't really need a pallet for that, but we might as well. But, definitely don't need a pallet for the final single brick. And he said, now, Rico, what I plan on doing is I want to palletize all of these things, and I will give you flags. Whenever a customer comes, I would like you to put flags in the pallets that I need to move for you, and I will use my new handy-dandy forklift, high-tech there, to move these pallets out to the clients, and they will be much happier. So Rico decides to try it out. Ching, 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 ching. The metal gate right there moves back up, and oh, I wiped out our building. Hang on. Metal gate moves back up, and the client is still sitting there waiting for this whole palletizing process. He says, I still need my 210 bricks. So Rico grabs his flag, and he says, all right, well, I'll stick one in the pallet of 128. So we'll take 210 minus 128. Borrow the 1, 2, 1. Oh, by the way, as I do this, I should mention that if you are planning on taking the Cisco exam, there are no calculators allowed on Cisco exams at all. So if you haven't done longhand subtraction, division, basic math skills for a little while, you may want to practice those. I had a rude awakening when I got into a Cisco exam and had to do longhand division, and I thought, I have completely forgotten how to do this. The calculators make you stupid. So we've got the first pallet is now fulfilled. I've got the second pallet. Take off our 64 bricks, subtract that out. Got 9, 8, 12, 8, so 28 left over. Don't want to give too much, so we won't put a flag in pallet of 32. Put a flag in 16. That would be 12. So a flag in the 8. And the 4, there's our subtraction that will give us 12. No flags in 2, and it's not bonus brick day, so we will not put 1 in 1. And there we have it. Bob grabs his forklift and now scoots this pallet out, and we have a much happier customer group. Now, unbeknownst to them at the time, Rico and Bob had actually invented a system to convert to binary. This is the way computers actually handle numbers. When we see the number 210, the computer actually sees bits. Do you remember we talked about early on in the video, or not this video, but the series, we talked about how the computers and networks handle size, and I talked about bytes going to kilobytes and megabytes and gigabytes and so on. But I said there was one thing smaller than a byte, and that is a bit. Now, do you remember how many bits are in a byte? 8. So if we have 8 bits in a byte, notice, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8 different numbers that we have right there. Those 8 numbers represent the 8 bits. So when we see the number 210, behind the scenes, the computer actually sees 1, 1, wherever you see the flags, that's where the ones are, 0, because we don't have a flag in the 32, 1, 1, 1, 0, 0. That is the binary equivalent of 210. Now, this skill that I'm showing you right now is essential when you are learning to work with subnetting. So let's do another. We have this client right here that says, I would like 120. So we'll just imagine those flags aren't there because I can't think of a quick, easy way to delete them. And I'll take 120. First, we'll have black flags. First flag goes in. Oh, what am I thinking? 120. You can't subtract 128 from that. So our first flag will go into 64. So 64, subtract that out. 2, 1, that'd be 6, 1, 0, 56. So our second flag, 32. 32 minus equals 4, 2, 24. So we have a flag in 16 and a flag in 8. If you subtract 16, that'll give you 8, and subtract 8, that'll give you 0. We've done it. So the binary equivalent of 120 is really 0, 1, 1, 1, 1, 0, 0, 0. Sorry, with all those flags, it's starting to look confusing. I'll clear that off in just a moment. Now, when you're practicing the skill, and I have a practice slide coming up right after this, I want to show you how you can actually check your work using the Windows calculator. In Windows, if you click on Start and go to Run and type in Calc, C-A-L-C, the first 4 letters of calculator, you'll get this guy popping up. Now, you'll want to make sure that your view is set to scientific, not standard, because standard won't let you do it. That's the standard. This is scientific. So if you want to know what a binary equivalent, we'll do 210 first. You just type in 210. That's the decimal version. You can see the bullet decimal right there. And just click this bullet over to binary. Ka-chunk. That is the binary equivalent of, holy cow. Did I do that wrong? Did I subtract incorrectly? No. Yes. No. Yes, I must have. See, and this is why we check our work. Jeremy must have gone too fast in his subtraction skills. So hang on, let's verify this, because I'm sure many of you were like, no, that's not it. 210. First flag. I've got flags going everywhere. 128. Subtract that out. 1, 0, that'd be 2. 82. Ah! I came up with 92. Idiot! Can't believe that. So 82 minus 64. I feel silly right now. 18, right? So no 32s. 16. Am I on the right track here? Hang on. I am. Okay. Sorry, I had to look at the calculator to make sure I had that funny wrong feeling. So 18 minus 16 is 2, so our last flag goes in the 2. So forgive the scribbles, but the binary equivalent should be 1, 1, 0, no 32s, 1, 16, no 8s, no 4s, 1, 2, no 1s. And that is what it shows right here. Perfect. and I'm glad I showed you how to check that so that you guys don't think I'm crazy. All right, so let's just double check 120 now. I'm going to put 120 as our decimal number and go to binary. And we can see, okay, I know you're thinking, it was wrong again, but notice that Windows will strip off the leading 0. Notice we only have 7 bits. So 0, look right to left on my figure right here. 000, that's correct. 1111, that's our 4 ones right there. And the calculator doesn't show the 0, but I do because I'm working with a full 8 bits. Windows will strip off any leading zeros that you have. So we did 120 correctly. So let me take you to a slide where we can work through a few more examples. So as the final slide I have for you is a little binary homework. What I would like you to do is watch the initial part where I get just set up to do this, but then pause the video. And I want you to just grab a piece of paper and try working through these on your own, and then come back and I'll work through them with you to show you how to work through each one. The first thing that you want to do whenever you're getting ready to convert to binary is to write up your palatized values. Just at the top of your paper, start from the right to left because it's easier that way. You just start with 1 and start multiplying by 2. 2, 4, 8, 16, 32, 64, 128. That is our 8 binary values that we always use when we're converting numbers to binary. Now, technically, these are powers of 2. 2 to the power of 0 is 1. Anything to the power of 0 is 1. I actually had somebody try and explain to me why that is one time, and to this day I can just say anything to the power of 0 is 1. I'm not too sure exactly why the mathematical formula behind that works that way, but that's how it works. Anything times 0 is 0, but anything to the power of 0 is 1. So 2 to the power of 1 is 2. That's just 1, 2. 2 to the power of 2, that's 2 2's. 2 times 2 is 4. So these are all just powers of 2, and that's how we come up with these different numbers. Now, that fact will come into a huge play later on when we get into subnetting at full bore. So go ahead and pause the video if you'd like to work through these, because I'm going to start with number 1 right here. We have the number 180, and we need to convert that to binary. So start off, pause if you're going to pause. If you're going to watch, go ahead. 180. I'll put my first 1 right there. Don't need flags anymore. I bet you that's what goofs me up last time. So there's my excuse. So I borrow the 1. We've got 2, 52. Can't take a 64, so 32. Subtract that out, and we have 0, 20. So 116 and 1, 4 will give us 20. The binary equivalent of 180 is 10110100. See, now I'm all nervous after that last mishap. So I'm going to just make sure. 180 in binary, chunk. We've got 101101. Good. Okay. Okay. I feel confident without checking my work now. I feel a little better. All right. So that is the first one. Second one, 41 into binary. So I'll just keep these up here and work below. 41, I'll say 0, 0, 1. That's where our first subtraction can come in. 41 minus 32 is 3, 9. So we have 9 left over. 0, 1, 0, 0, 1. Just 8 and a 1 will give us our 9. Subtract that out, we have 0. So the binary equivalent of 41 should be 00101001. All right. Now that's converting decimal to binary. Now, using that skill in reverse, you should be able to convert backwards, meaning take the decimal values and convert them back into binary. So let me just wipe off some of our scratch work right there. And I'm going to start off with this one. It says take 00110110 and convert that to decimal. All I need to do is put those values back up underneath our binary chart here, and then just do some addition. I'm going to take 32 plus 16 plus 4 plus 2. And that will give us our decimal value. So we've got 6 and 4 is 10, 2 and 2 is 4, so that will be 14, carry the 1, and 54. So that binary value is actually 54 in decimal. One more, we'll take this one. We've got 128. Instead of lining them all up, I'll do it a little quicker. No 64s, no 32s, 116, no 8, no, and then we have a 4 and a 2. Add those up. We've got 20. Carry the 2, 5, 150. So that is a decimal value is 150. I would encourage you, if you feel weak on this, take any value. from 0 to 255 in decimal and convert it to binary numbers and just make up values in binary and try and convert them back to decimal. By the way, before we wrap this video up, one thing I want to mention is in our IP addresses, you notice that these numbers can only go from 0 to 255. Now you know why. We have 1 byte of information in each one of those octets in our IP address, right? If you were to change all of these to 1, meaning turn them all in, you have a binary value of all ones, what do you think you would get if you converted that back to decimal? That's it. 255. That's the biggest number that we can get by using only 1 byte of information. So that is the reason why our IP addresses only can go from 0 to 255. Let's review. What we did as we walked into this video was start off by a review of TCP/IP, just the basics of what an IP address was, what it's used for, and so on. I then gave a sneak peek of what's to come with TCP/IP version 6, and even gave a bonus conspiracy theory on top of it all. But the essential skill that hopefully you've mastered by this point is converting numbers from decimal to binary and back. That skill is one of the foundation pieces that you'll need as we get more into advanced subnetting. I hope this has been informative for you, and I'd like to thank you for viewing.